So I'm really glad to be here to talk about the Bloomberg Supermicro hardware implants. We're 1 year on, and unfortunately, I have to start this talk with the same disclaimer that I still don't know the story behind the story. We don't know what happened with these hardware implants, but what I do know is a lot about firmware and hardware security. I've been working in this field for many years, starting with the Thunderstrike firmware vulnerability on MacBooks, Thunderstrike 2. I've also been thinking a lot about how do we build more secure systems with commodity hardware, with the Heads firmware project, and also the Linux Boot firmware project in collaboration with Google and Facebook for building more secure servers. So when the Bloomberg story came out in October of last year, I was really interested about because these are the sorts of things that we've been thinking about. How do we defend against? And the part that I found really interesting was in this photo illustration. They highlight a part of the board that is exactly where I would put a hardware implant if I were to build one that interfaced with the BMC. So that lended some credibility to the story to me, at least the technical feasibility of it. And a lot of other folks in the security community had very similar views. Matthew Garrett said, of course, if you want to target servers, the BMC is the right place to do it. Senrio said, yes, the supply chains are a weak link in building these sorts of systems. But not everyone thought that this was plausible. And we spent a lot of time sort of debating what was going on with this story. So let's have a quick review, because it has been a year, about what Bloomberg alleged in the big hack story. So the key claims that they made were that Amazon found something on a Supermicro server that they sent to a tester about the size of a grain of rice that looked like a signal conditioning coupler on the main board that was not part of the original design, and that this connected to the baseboard management controller, and it was able to give the attackers access to the system even when it was crashed or turned off. And that last part sounds a little kind of hyperbolic, that if the machine is crashed or turned off, you wouldn't expect an attacker to be able to do anything. Except that's what the baseboard management controller does. The BMC runs even when the main CPU is turned off. In fact, it's connected to the power supply and is what turns the system on when you want it to cycle power. And because you want to be able to cycle servers remotely, it's connected to the network. It also provides access to the serial console of the machine, so you can do BIOS updates and things. Most of them also have a USB interface, so they can provide file systems to do unattended operating system installs. A lot of people want to use their servers with remote consoles, so they tend to have VGA, which means they have PCIe access, which means they can also do direct memory access to the host memory. Many of them are also muxed into the SPI bus that the x86 firmware is stored on, which means they can potentially change the firmware that the system runs at boot. And a lot of them are also muxed into the LPC, which gives them access to secrets that are sealed in the TPM. So this device is connected to every important piece of the server. And we would hope that it would be one of the most hardened, locked down parts of the system. Unfortunately, it's not. As the Azure security program manager points out, the BMCs are typically insecure. They have no protection against unauthorized updates. They typically have no ability for the user to run code on them to even detect if an attack has happened. And they have no way to recover from one of these sorts of attacks. And additionally, they typically don't participate in any sort of remote attestation. So there's no way for them to prove what they're running. And that's a really bad situation for such an important piece of the system. So going back to the Bloomberg article, they also claim that there were 30 companies affected, including Apple. and that Apple had independently found a problem with Supermicro and reported it to the FBI, and that Apple had removed Supermicro from their supplier list. Again, these are the allegations from the article, but this does tie into a story that came out back in 2016, 2017, that Apple had dumped Supermicro as a supplier. There were never any further updates as to what happened there, but it potentially provides some corroboration to the story. So, last set of claims in the article was that some of the systems were embedded between layers in the PCB, and we'll talk a little bit about what that would mean. And then also that the Chinese People's Liberation Army was in charge of building this attack and subverting Supermicro. And that's where there's potentially some geopolitics involved. And again, I don't know anything about that side of it. I'm just looking at the technical feasibility. So considering how explosive those claims are, we would hope they'd be really well sourced. Bloomberg says they have 17 anonymous sources, including national security officials, people inside of AWS, and senior insiders at Apple. Bloomberg continues to stand by their story. The editors claim to have spoken with these sources and to trust them. But publicly, it's a different story. Everyone involved and named in the story has denied it. The Office of Directorate of National Intelligence said that they've seen no evidence of a supply chain hack. AWS wrote on their blog that they've at no time have they found anything with Supermicro, and they've not engaged in any investigations with the government. Apple was even more blunt, with Tim Cook saying there is no truth to this story. So it seems like the people involved are vehemently denying it. Bloomberg standing by it. Again, we don't know what's happening behind that story, but we can look at the technical side. And Supermicro CEO wrote a 2-page letter in which he addressed some of the technical issues. He talked about that things that they've done in their manufacturing process to try to prevent unauthorized alteration of the boards, as well as ways that they could detect these alterations. And when a PCB is manufactured, this is not Supermicro's facility. This is a small contract manufacturer I visited in Shenzhen to try to understand how PCBs are made. The process starts with these bare copper boards that have holes drilled in them for where components or signals have to be routed, that are then electroplated, and then the actual connections are etched onto the board. And these bare boards are then optically scanned to verify that all of the connections that are supposed to be there are there, and that there are no breaks in any of the wires. If someone wanted to subvert this process, they would have to both modify the drill files or the mask images, as well as the verification. So that's quite a few different contractors who would have to be involved in that process. Those bare boards are then laminated together in different layers. So if a part were to be inserted inside, it would have to be done at this stage. And the boards, once they're laminated, they're then tested either with a flying probe or a bed of nails to verify that all of the multi-layer connections are present. So if there's any part that has changed the connectivity by virtue of being laminated in there, it would be detected in these stages. And so that's yet another set of contractors that would have to be subverted. That it's not outside the realm of reason, but it's also really bad for being able to have any sort of cover story. Because if it happens at any of these stages, it would be obvious who was involved. It's also really bad for containment, because at this point it's not known where these boards are going to go. So they would have to be installing them in almost all of them to be able to ensure that they've reached their targets. Going back to the Supermicro letter, they also point out that they have employees on site with the companies when these things are being manufactured. And what I found in Shenzhen was that most of the companies I talked to also sent people into the clean rooms of the manufacturing facilities to watch the process, where the parts are being installed on the boards, and they're sent through the surface mount assembly lines. The reason most companies are doing this is not for security, but what they're concerned about is the quality and the sources of the parts. Most of these surface mount parts are bought in bulk by the contract manufacturer, and it's not always clear where they're coming from. That in China, you can find a lot of places that are taking scrap electronics, desoldering the components, and then selling them by the kilo in some of these markets. And these secondhand parts tend to be of lower quality, probably not going to be sabotaged, but it's a concern for the reliability for the manufacturers. There's also a lot of counterfeit parts that are being made just to reduce the price for the contract manufacturers. The FTDI serial chips a few years ago were being counterfeited very heavily. In fact, this to the point where the FTDI driver manufacturer was trying to detect and brick the counterfeit ones. The folks at Zeptobars decapsulated the chips and found that the counterfeits are not even built on the same die. They have a completely different CPU architecture that is running software that's pretending to be the original. And this was affecting hundreds of manufacturers. So it is definitely feasible for counterfeits to end up in the supply chain. The CEO continues that they do x-rays of their main boards, which would detect any sort of parts laminated inside. And it's pretty neat what you can see on when you x-ray a system. Active components like chips tend to be pretty obvious and fairly easy to distinguish from passives like SMD resistors or capacitors. So if somebody had tried to disguise something as a signal conditioning coupler, it would show up differently in this X-ray. Now, occasionally you do find interesting parts inside of packages, such as these Ethernet magnetics that have inductors, actually encased in epoxy. And occasionally people will decapsulate those chips and wonder if there's some sort of implant. But it's a fairly standard for certain parts to be made that way. One problem is that we don't necessarily know what is supposed to be on the board as an end customer. Sophia de Antoine's company, Riverloop, did a teardown of a bunch of Supermicro boards, trying to identify, essentially to reverse engineer the schematic and try to understand what parts were supposed to be there. And they found a few places where things seemed out of place. Either the markings on the board didn't match the parts, and it appeared mostly to be a case where the manufacturer had revved the design but not changed the silkscreen. You can check out her blog post about it for some more details. Okay, the big thing that Supermicro points out in their letter is that they're talking about the manufacturing process. They're talking about how do they deal with the assembly process. And they're looking at how do they, as OEMs, detect things being installed. And this is where I agree with Supermicro. I think it's very unlikely that someone would be able to subvert them at that level, because it's difficult to know where the boards are going to go. I think what's much more likely is what we saw in the Snowden documents, where intelligence agencies are intercepting shipments of computers and opening up the packages, installing hardware implants and things, and then having them continue on their way to the customer. In fact, the NSA has an entire catalog of these interesting parts that can either JTAG the CPU during the boot process, things that are embedded in Ethernet jacks to be able to intercept data. They have firmware attacks that will modify the BIOS. They have attacks that will use SMM to be able to hide from detection. And in general, these sort of tailored access operations are ideal for being able to contain it to a single customer, to be able to conceal it through some different means. And also, it's a much better cover story, because if they're found, it's not as obvious as something laminated between the circuit board that had to have happened at point of manufacturing. These sort of TAO hardware bugs could have been installed at any point. So one last thing in the Supermicro letter is that they think that it's highly unlikely that any altered board would function properly because the attacker would lack complete knowledge of the design. And now I disagree strongly with Supermicro on this because I don't have the schematic for their board. I don't have complete knowledge, but I've been able to build exactly the sort of implants that are described here. And that's because these systems are built with commodity parts. So the BMC boots off a SPI flash that is a off-the-shelf part, and we can pull up the data sheet, and we can understand how it's connected to the BMC. And the one that we're most concerned with is this serial out line that goes to the BMC from A-speed here via a small series resistor that essentially could be considered a signal conditioning component. And I've been able to build a device that replaces that part of the system on a somewhat older Supermicro board connected to the flash with a small FPGA. And it's able to replace the data as it's being read by the BMC. You might think, well, that resistor is pretty small. But Moore's law has let us build really small CPUs. That if we look at a computer from a few years ago, the CPU was about 21 square millimeters. If we zoom in on one of these transistors, we can actually see the individual transistors, and we could fit an entire ARM Cortex-M0 in the space of 2 transistors from just a few years ago. So fitting a full CPU into a 0603 resistor is completely within the realm of possibility. Mine's a little bit larger. I'm using an off-the-shelf FPGA board, but I also don't have the backing of a nation state for building this this proof of concept. So, but unfortunately, fitting in that small 2-pin part does give us a lot of limitations and a lot of challenges. Typically, the SPI chip has 6 or more wires, but we don't have power and ground. So we have to power our device parasitically based on the current flowing through that pin. We don't have the chip select line, so we have to be able to detect when the BMC is reading from the flash based on just signals going through. We also don't have the serial data input line, so we don't know what addresses are being read from the chip. We have to watch for patterns. We also don't have the clock line, so we have to run a PLL to try to synchronize from the data stream. And additionally, we can't generate arbitrary data streams. We can only turn 1 bits into 0 bits by disconnecting the line. And when it floats, it gets read as a 0 by the BMC if the timing works out and a bunch of other things. It's pretty flaky. For detecting the clock, we watch for 0101 or 1010 bit patterns in the bit stream, and then we're able to run a PLL that allows us to clock to that. For the proof of concept, I had to lock the SPI flash to the slowest speed at 12 megahertz. Again, this is a zero budget sort of project. So next, we need to figure out where can we put this in the flash. If we boot the BMC in with the debug console, it actually prints out a nice message that shows us how the flash is organized. It has the U-boot bootloader It has the compressed kernel. It has the root file system, which is also compressed. And unfortunately, all that compressed data is a mix of 0 and 1s. So we can't really try to override that very easily. But there's some very white parts of it, which are all 1. And it turns out that's the JFFS2 that stores the non-volatile configuration data. And if we hex dump it, we see it's mostly all Fs, which gives us lots of 1s to work with. And these blocks have an easily identifiable header that we can detect in the bit stream. So by watching for this magic bit mask. And when we see that being read, it's possible to substitute our own data. In this case, we can put a little bit of a shell script in there. And when the BMC is booting, it will actually execute that shell script for us. So let's have a quick demo. This is going to be a video because I don't have any hardware with me. And it also was really flaky. It was like 1 in 10, 1 in 20 times it would actually work. So we're going to do a video demo. So we're running in QEMU in this case. And when the system starts up, we can see on the left-hand side, it's printed out the console from the FPGA, that it's synchronized the PLL. And then when the Linux kernel starts up, it's going to mount the JFFS2 at some point. OK, and then we've seen the magic header. So it has been provided with the hacked NVRAM. And now the BMC takes a little while to start up. If you've worked on servers, you know how frustrating it is that for whatever reason they take quite some time to boot. We also get a bunch of kernel error messages that I think are due to the fact that QEMU doesn't have all the hardware available. But at this point, yeah, the FPGA has nothing else to do because everything's been read from the flash. So it's just now in the hands of the Linux kernel. OK, which is now going to bring up the interface once it tries to do DHCP. And it doesn't get a response. And all right. And we get our hello world message out from it. Now, it turns out this is actually the hard way to do it. That if we just wait a little bit longer, the BMC prints this message. And if you hit enter, it just drops you to a root shell. So all of this work, for actually fitting inside that coupler and trying to do all that clock reconstruction, it turns out there was an easier way. But I was trying to do this based on what was in the Bloomberg story, and it was a fun exercise. And it turns out that most boards have headers or unpopulated pins for the BMC that you can probe with an oscilloscope, and you'll find what looks like a 115 kilobaud signal on it. And it turns out that on pretty much all of the A-speed BMCs, they have the same function that you can just send enter and start running commands as root. So someone with physical access could potentially do that. And this is something where it would be very easy to add post-manufacturing as the system is being shipped. So what are some things we could do to try to detect these sorts of implants? Well, a lot of high assurance sites will replace the flash chips with ones of their own. But because this implant isn't in the flash chip, that's not going to do it. Trying to read the data from the flash chip won't reveal the implant, both because the reader doesn't execute the same sort of pattern of reads as the main CPU, and also because we're typically on the other side of the bus, other side of the series resistor from the reader. You might hook up a logic analyzer and try to watch all the data coming out from the SPI bus, but because, as I mentioned, we're on the other side of that series resistor, the logic analyzer won't see the modified data. A lot of people have suggested that if you run network capture on the BMC interface, you'll see the exfil or something from it. But that not all attacks are going to exfil on the BMC interface. There's a really wonderful one proposed at DEF CON a few years ago by Intel ATR that allowed the BMC to install a modified SMM that could then hook the hypervisor, which would allow any guest on the machine to, if it knew how to talk to the SMM, to be able to read every other guest's memory. So in that case, then a co-tenant would be able to exfil the data through the normal network interfaces and without the BMC being involved at all. So what are some things we can do to try to improve the situation? The big problem is the BMC is vastly overpowered. And if we freeze frame that video, you might have noticed that it's booting a 2628 kernel, which was released over 10 years ago. And you think, OK, this is old hardware. This is the report came out a year ago. Surely it's better. Well, I just updated the BMC to the latest version, and it's now 2628. So this kernel has major remote execution CVEs for it that are still just waiting out there. In fact, occasionally I've had vendors tell me that going after BMC vulnerabilities is unsporting because they're just made of security holes. And we've seen a lot of new ones coming out between the pants down vulnerability that allowed a guest to talk to the BMC and get basically arbitrary read, write of everything in physical memory, to the recent publication from Eclipsium that showed how they could use BMCs to present alternate boot media and take over systems. And I don't mean to pick too much on the BMC. These sorts of firmware issues are on all sorts of other systems as well. I've taken the research I did to build this proof of concept. I've also used in a similar way to attack Intel BootGuard, which gave us a bypass of the hardware-rooted trust on x86. And I've also turned it into an open source tool for doing SPI flash emulation. And this has revealed that lots of ARM CPUs have similar issues. Folks have gone after the PSP with this sort of tool. And the big problem is that our computers are not a single computer anymore, that they are built out of lots of other pieces that all have their own code. And we need to start treating them as mutually untrusted components. If we look at a modern server, pretty much anything more complicated than a resistor has some sort of firmware. The RAID controller has firmware. The NIC has firmware. The video card has firmware. The drives have firmware. The fans on some of these systems have firmware. The power supplies have firmware. In fact, on this particular system, I was able to modify the firmware in the power supply that was able to then fuzz the BMC and get code execution on the BMC from the field replaceable power supply. And that's a big problem, that these devices are assuming that the other hardware in the system can be trusted. And these are not big attacks. These are, these are not multi-million euro attacks. These are, 5-10 euro attacks, which Joe Fitz gave a really good talk about, where they had looked at literally duct taping Raspberry Pis inside of servers shipped to companies who had no idea how to detect them. Joe also made these wonderful stickers, and he sent me with a bunch of them. So if you want some I Want to Believe stickers, I have them afterwards. I'm really encouraged that NIST has started pushing for folks to start thinking about systems as more of these interconnected networks. And most of their guidelines have to do with measuring things into the TPM. And these trusted platform modules are a good step forward to be able to move the root of trust into a much simpler sort of device. but they are not a solution unto themselves because, as the TPM genie showed, hardware attacks against against TPMs give the ability to circumvent the root of trust there as well. So we have to really start thinking about what is the bigger picture. Some people are proposing that we should move things into these trusted execution environments like SGX or Trust Zone. And a lot of manufacturers are also starting to include new roots of trust. Chromebooks and Google servers have a security coprocessor called the Titan. Microsoft has proposed their Cerberus on Azure. And then Apple is shipping the T2 on their hardware. And all of these are ways to try to move the root of trust out of out of this this mutable firmware into some other hardware-rooted system. And people keep finding vulnerabilities in them, but again, it's a step in the right direction. But the big solution, I think, is we also need far fewer secrets in our systems, especially in our boot process. And I'm encouraged that the open hardware movement and the open compute movement is starting to build servers that where the manufacturers are publishing the schematics. So if you buy a Leopard mainboard, you get a full schematic with it. And this allows a motivated customer to verify that what is built is what is actually in the design, that they can start to reason about why are these different pieces connected and what are the capabilities that gives them. Most of these open compute machines are also running OpenBMC, which allows us to use a modern Linux kernel where we can update it according to our own schedule rather than being dependent on the OEM to do so. Samantha Brown gave a wonderful talk at OSFC last year about how OpenBMC makes for a more resilient system. Ron Minnick from Google took a slightly stronger position that we need to be building all of our firmware with Linux and open source. He and I are working together on the Linux Boot project, which is trying to make more secure, more flexible, more resilient systems by building the firmware with, the boot firmware in the SPI flash out of Linux. The MicroBMC project has taken the work we've done on Linux Boot and brought that into the ARM A-Speed CPUs, and they now support Supermicro boards. So if you want to replace your 2.6 kernel with a modern, I think this is a 5.4 kernel, you can do that. And the real advantage in doing this is we get open source, we can reproducibly build it, we can have it participate in remote attestation to prove what it's running. We can write these things in safer languages. MicroBMC is entirely in Go, so we don't have to worry about memory corruption errors the same way we do with the C ones. And we also can discard a lot of the legacy features. Things like the pants down and USB Anywhere are taking advantage of things that most customers don't need in their BMC, but are still there for legacy reasons. So here we are 1 year later. We still don't know if the big hack really occurred, but I hope I've shown you that it is technically feasible for these sorts of implants to happen. And I hope that we do have a way forward through open hardware with hardware roots of trust and remote attestation. You can check out the slides from this talk on my website, and I'd love to answer any questions, and I'll also be around the next 2 days and love to chat further about it. Thank you.